Good morning, dear students. Today I have made this presentation more interesting to all of you. I hope all of you will like it. So before starting, do you know each hydrogen atom in your body is likely 13.5 billion years old, as they were created at the birth of the universe. So let us start with today's discussion on the topic structure of atom. So today we are going to discuss about Planck's quantum theory, including the explanation of black body radiation and photoelectric effects and dual nature of electromagnetic radiation, that is particle as well as wave nature. So first one is particle nature of electromagnetic radiation, that is Planck's quantum theory. So we are knowing that after electromagnetic wave theory, Max Planck in 1900 put forward a theory known after his name as Planck's quantum theory. This theory was further extended by Einstein in 1905. So these are some of the main points of this theory, which are as follows. And this theory was also given to explain the phenomenon of black body radiation and photoelectric effect to get it more clear. So let us have a look on the main points of this theory. So first one is that the radiant energy is emitted or absorbed not continuously but discontinuously in the form of small discrete packets of energy. Each such packet of energy is called a quantum. In case of light, the quantum of energy is called a photon. Now the second one, the energy of each quantum is directly proportional to the frequency of the radiation. That is, E is directly proportional to nu. E is equals to, that implies E is equals to h nu, where h is the proportionality constant called Planck's constant. Its value is approximately equals to 6.626 into 10 to the power minus 34 joule second. So this is Planck's constant, small h. Now the third one is the total amount of energy emitted or absorbed by a body will be some whole number quanta. That is, E is equals to nh nu, where n is any integer 1, 2, 3, and E you are knowing it's the energy of each quantum, and h is Planck's constant and nu is the frequency of radiation. Now these are some of the important main points of Planck's quantum theory, which was put forward by Max Planck in 1900. So after this, there is some explanation of black body radiation and photoelectric effect by the use of Planck's quantum theory. So first one is explanation of black body radiation. So how it had explained that? It explained that when some solid substance is heated, the atoms of the substance are set into oscillation and emit radiation of frequency nu. Now, as heating is continued, more and more energy is being absorbed by the atoms and they emit radiations of higher and higher frequency. So as red light has minimum frequency and maximum wavelength, and yellow light has higher frequency, therefore the body on heating becomes red, then yellow, and so on. So this is how Planck's quantum theory explained the black body radiation. And you are knowing what is black body. So let us proceed. Let us discuss how Planck's quantum theory explained the photoelectric phenomenon. So for explaining it, Einstein in 1905 was able to give an explanation of the different points of the photoelectric effect using this theory, which are as under. So first one is when light of, what he had explained, that when light of some particular frequency falls on the surface of a metal, the photon gives its entire energy to the electron of the metal atom, and the electron will be detached from the metal atom only if the energy of the photon is sufficient to overcome the force of attraction of the electrons by the nucleus. That is why photoelectrons are ejected. You are knowing what are photoelectrons. So that is why photoelectrons are ejected only when the incident light has a certain minimum frequency called threshold frequency, that is nu naught. So this is the first explanation part. Now moving further, he further explained that if the frequency of the incident light, that is nu, is more than the threshold frequency, that is nu naught, the excess energy you are knowing E is equals to h nu. So here the excess energy will be h nu minus h nu naught is imparted. This excess energy is imparted to the electron as kinetic energy. That is, we can write it as kinetic energy of the ejected electron will be equals to half mv square, which will be equals to h nu minus h nu naught. You can see over here the equations are given. So we can rearrange it as h nu will be equals to h nu naught plus half mv square, or we can write h nu naught as w naught, that is work function, plus half mv square. So we can call this equation as Einstein photoelectric equation. So now we can say that hence greater is the frequency of the incident light, greater is the kinetic energy of the emitted electrons. So he further explained photoelectric effect as increasing the intensity of the light of a given frequency increases the number of photons, but it does not increase the energies of the photons. So hence we can say that when the intensity of light is increased, more electrons are ejected, but energies of these electrons will not be changed. So you should keep in your mind the energy acquired by an electron when it is accelerated through a potential difference of 1 volt is called 1 electron volt. We can write its unit in electron volt, and 1 electron volt will be equals to charge on 1 electron multiplied with 1 volt. So charge on electron you are knowing 1.602 into 10 to the power minus 19. So multiplied with 1 volt. So we are getting 1 electron volt will be equals to 1.602 into 10 to the power minus 19 joules. So I hope now it's clear to all of you how by using Planck's quantum theory the photoelectric effect was explained by Einstein in 1905. So now moving further, dual nature of electromagnetic radiation. So from the above discussion, we have discussed now the Planck's quantum theory and explanation part of black body radiation as well as photoelectric effect. So from this very discussion, we conclude that some properties of light, or in general any radiation like interference, diffraction, etc., can be explained only if we consider light to have wave nature, whereas some other properties of light or any other radiation such as black body and photoelectric effect can be explained if we consider light to have a particle nature. So thus we can say that light is said to have a dual nature, that is it behaves as a wave and as well as it behaves as a stream of particles. You can see over here the particle nature and wave nature of light. So now these ideas were further put forward by Einstein in 1905. So this is all about the dual nature of electromagnetic nature. You will read about the duality of the electromagnetic radiation later on in higher classes. So let us solve some questions now. The first question is that the threshold frequency nu naught for a metal is 7 into 10 to the power 14 per second. The threshold frequency is being given to you, and now you have to calculate the kinetic energy of an electron emitted when radiation of frequency nu, that is nu is given to you, that is 1 into 10 to the power 15 per second, hits this metal. Yeah, I hope you have understood the question. So now here what we have to calculate, the kinetic energy of the electron emitted. So here we have been given nu and nu naught. So now applying the Einstein equation, and what was that Einstein equation? That is half mv square will be equals to h nu minus h nu naught. So applying that equation over here, so we can write it as half mv square will be equals to h, we have taken h as common, nu minus nu naught. So now substituting the values over here, we are knowing the value of h, that is h is Planck's constant, and that is the having the constant value 6.626 into 10 to the power minus 34 joule second. And nu naught we have been given in the question. So we, after putting that and after subtracting nu minus nu naught, we are getting 3 into 10 to the power 14 per second. And then after multiplying it with Planck's constant, then we are getting our answer, that is we are getting our kinetic energy of the photoelectron emitted, that is 19.88 into 10 to the power minus 20 joules, or we can write it in standard form, that is 1.988 into 10 to the power minus 19 joules. I hope you have understood this question. So let us proceed towards our next question. So next question is like this: a 100-watt bulb emits monochromatic light of wavelength 400 nanometers. Now you have to calculate the number of photons emitted per second by the bulb. So here you have to calculate the number of photons emitted. So for calculating it, what the things we have been given? Power of the bulb, that is 100 watt. So we can write 100 watt as 100 joule per second, because we are knowing power is equals to energy by time. So that is 100 joule per second. So after writing that, we can write energy of one photon will be E will be equals to h nu, and nu means c upon lambda, means velocity of light divided by wavelength. So now the E will be equals to hc divided by lambda. So after substituting these values over here, h we are knowing here it is Planck's constant, c is also having constant value, that is 3 into 10 to the power 8 meter per second, and upon dividing the wavelength also being given to us, that is 400 nanometers. So we can write it as in terms of meter. So we can write 400 into 10 to the power minus 9 meters. So after calculating this term hc upon lambda, we are getting the value 4.969 multiplied with 10 to the power minus 19 joules. Now this energy, we have got energy of one photon. So after getting the energy of one photon, we have to calculate the number of photons emitted. So for calculating the number of photons emitted, we have to divide the total energy, that is the power of the bulb, divided by the energy, that is the power of one photon. So we are dividing the total power of the bulb, that is 100 joule per second, divided by 4.969 into 10 to the power minus 19 joules. So after dividing, we are getting 2.012 into 10 to the power 20 per second. So we can, now I hope you have understood that how we have calculated the number of photons emitted per second by the bulb. So today we have discussed about Planck's quantum theory, including the explanation part of black body radiation and photoelectric effect. And we have also discussed about dual nature of electromagnetic radiation. So in our next class, we will discuss about emission and absorption spectra, including the continuous and line spectra. I hope you have understood. So thank you, students.